Welcome. All right. So today we're just going to keep going through time series. We're going to introduce a couple of other models that we could apply. Of course, I understand that that's not really going to make sense until we see it in action. We're going to look at some of the core ones on Friday. So I'll show you some linear regression, but there's lots of, you can just Google your way to it, but I'll show you how to do some linear regression and also some of these time series techniques. Okay? And so just as a little review, right, as a little review, make sure I'm recording, how quickly I forget. We looked at time series, which is when the X variable or the independent variable is a time variable. So when the independent variable, which of course is your X, is a time variable. Right, things like hours, days, quarters, etc. Should put etc. there because otherwise it looks like that's the list. That's not. There are many, many, many different types of ways that we can measure time. Okay, so a time series is what we're talking about. And what's different about time series is we have this dependency among the observations, right? So an observation in week 3 kind of depends on what happened in week 2, which also depends on what happened in week 1, right? And so now we have this time series, and so we have this dependency among observations, right? And so with time as an independent variable, we can no longer assume that observations are independent, right? And so we need tools to deal with that. So we can no longer assume observations are independent. So we're developing methods to deal with that. So we are developing methods to deal with that. So good. We started talking about, okay, well, once we've identified, what's going on in there, is there just a horizontal trend or sorry, a horizontal pattern? I shouldn't say trend because a trend means it's either going up or going down or something like that. So is there some sort of shape? Right, but is there a horizontal pattern where you've just got activity kind of moving on the horizontal, or do you have some sort of skip at some point where it moves to a different level? You can look and see seasonality, right? So maybe things are kind of following this seasonal pattern that you need to incorporate into your model. Cyclical models go beyond a year, so you might have this kind of up-down pattern, right? But they don't necessarily, they're not restricted to a year, right? And so that would be a cyclical pattern. And then you can have combinations of, you could have some sort of seasonality and maybe some upward trend, right? So there is seasonality here, but it's also moving up, 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 right? And so we need to be able to recognize those patterns, right? And we also need to know which models to apply when we see those patterns, right? So we also after plotting the response variable, which is going to be your y variable against time, which is your x, of course. Okay. We try to identify the appropriate pattern, or we try to identify a pattern, right? So it could be horizontal, it could be a trend, it could be seasonal, it could be cyclical, or any combination of these. Okay. There's probably other patterns too, but we're going to focus on these ones. And so depending on the pattern that you see, right, that's going to determine what the appropriate forecasting method is. Okay. So depending on maybe I'll say the pattern will determine what forecasting method is appropriate. Okay, and we're going to keep looking at some other forecasting methods. But to identify a good forecasting method, right? And so we looked at the naive forecasting method the other day, and we looked at the running average, right? The running mean forecast. So we've already seen two forecasting methods, and they were only for horizontal trends, right? Today we're going to improve that. I don't think I talked about, I can't remember where I left off yesterday or the other day. Oh yeah, okay, we're good. It's where I thought we left off. Okay, so once we have a forecasting method, right, we look at things like the MAD or the MAE, the mean absolute error, or we look at, or we look at the mean squared error, but there's one that I'm forgetting. It is the MAPE, right, the percentage, right? And so to determine, I keep saying determine, but I'll stick to my guns. To determine which forecasting method is optimal, okay, is optimal or most accurate, we examine the forecast errors, right, which we said was the difference between the actual outcome and the forecasted outcome, right? So that seems fair enough, right? It does assume that we have the actual values, right? It's not, so if we're forecasting into the future, then that's a different thing, right? So here we have historical data that we're building a model, and then we're checking our forecasting abilities. So we examine the forecast errors, and we can look at things like, let me see here if I've got it handy. Doesn't look like I do. The MAE or the MAD, which is the mean absolute error or deviation. The MSE, which is the mean squared error. And the MAPE. Remember, the problem with the MAE and the mean squared error is that they're unit dependent, right? So it depends on what the units are. And then if the values are expected to be large, then of course these values will be large. That doesn't matter if you're comparing the same thing, right? Whereas the mean absolute percentage error, I think it is. I'll have to double check here. Phew. Mean absolute percentage error. Right, that one doesn't have any units besides percentage, right? And so so that might be nice if you're trying to compare overall, but usually you're comparing the same units. And so then usually what we do and what we're going to find today and solidify today is if you have to pick just one, use the mean squared error. Yeah. So here, if you have to pick just one, use the mean squared error or use the forecasting method that minimizes the mean squared error. Okay, so the mean squared error is going to be the moneymaker, and the other two will follow along, right? So if the errors are not bad, then of course all of these would be not that high. But if you have to pick one, right, then you're going to use the one that minimizes the mean squared error. And this note is new today, but I'll call it at the end of our review. Okay. Get back to where we were. Well, yeah, I bumped it down to a different page here, but hopefully that's okay. So let me just bring in this graph because we were talking about this graph at the very end last day as well. I keep forgetting what day of the week it is. So when I say last day, it's because I can't remember. I guess it was Monday. So, right, if we have a relationship like this, right, where we have blah, 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 and we have some random activity here, there doesn't seem to be any seasonality because we're looking at the first 11 weeks or so. I think so, right? Maybe even 12 weeks. Okay. And so it just seems to be kind of random activity. So we would call this a horizontal pattern, right? The thing is, then all of a sudden it skips up and it jumps up. So the sales increase, right? And so now we've got this step up and then we're moving on to another horizontal pattern. And so we talked about, okay, well, the naive forecasting method that we looked at, that just uses the previous value as its forecasted value, right? But that is naive, but it works, right? And so it would adjust relatively quickly here. Whereas if we use the running average, if you think about how an average works, right, it would take a long time for the running average to actually catch up here. Okay, and so what we're going to talk about now is our two main methods that we use for situations like this, where we have a horizontal pattern and potentially another horizontal pattern with kind of a step in between. So they're appropriate for a time series with a horizontal pattern. Okay. And yeah, these methods are capable of adapting well to changes in the level of a horizontal pattern, such as the one here. Now, so we're going to talk about moving averages and exponential smoothing. So we've already talked about the running average, and so kind of breezy introduction to the moving average, where we don't look at all the values. We might look at the most recent 3 values or 4 values or 5 values or 2 values, right? And so you would play around with that and until you find the method that minimizes your mean squared error. Okay. And so, and then exponential smoothing is another method that we haven't seen, and we're going to look at simple exponential smoothing. There are lots of other ones. So this moving averages and the exponential smoothing, those are kind of the base for a lot of other more complicated methods that we're not going to look into. But once you have these two under control, then you can go in and say, oh, it's just a tweak on the moving average. Oh, it's just a tweak on the exponential smoothing. So, all right. So one side note here, right? Unless you're making modifications, so which we can do, right? Then you shouldn't be using the moving average or the exponential smoothing when there's kind of a trend, right? So kind of an upward rise or a downward slope, I guess, if it's cyclical or if it's seasonal, right? So then we need other methods, which we're also going to talk about. Okay. All right. Oh, don't know why I went there. I went here. So let's talk about the moving averages. So the moving average is exactly what you probably think it is when you just think about moving averages, right? We take the most recent K data points. I don't know why I say data. I say data, but I read it weird. Right, and so we take the most recent K data. I said it again. Data points, data points. Now I've confused myself. And so we use those, the average of those K values to forecast for the next period. Okay. And so if we're doing a moving average of order K, which would be the K moving averages, so 3 moving average, 4 moving average, whatever. Then we take the sum of the most recent K data values, I don't know, and then divide by K, of course. All right. And so what happens is if you have, you know, a 3 moving average, then the first 3 values, you need those in order to build the forecast for the 4th value, right? And so you don't have a forecast for the first 3 values until you have the first 3, right? So it moves along, right? As you get another observation, then the average bumps down and you're always taking the average of, say, 3 numbers or in general K numbers, right? And so it would look something like this. Right, so notice if we have a 3-week moving average, then the first 3 weeks here, we need 3 weeks before we can get a forecast. Okay, and so that means that there are no forecasts. No forecasts. And thus no forecast errors, right? What is it? You can't lose if you don't play, right? That kind of deal. So no forecasts or no forecast errors for the first K observations. Okay. So then if we move, so if you take the average of 17, 21, and 19, you should get to 19. So then what we do is we move down one, and then we take the previous three, 21, 19, 23. Once we average those, we should get to 21. And so it keeps bumping down, bumping down, bumping down. Good. But it's lacking forecasts for the first K values. Okay. Oh yeah, here, I'll copy this in first. Maybe I'll make this a little bit smaller and just put it here. It's not terribly important, but it's fun to see a graph every now and then, right? And so if we look at the 3-week moving average forecast, right, then we see that we can't start until week 4. But if this is the forecast and this is what actually happened, then the difference between those two are the errors, right? The forecast errors. And so we see that these forecast errors are a little bit off, but then things kind of get better, right? And then here we're back to kind of a large forecast. Here the forecast was exactly right. That's awesome, right? And then a little bit off and a little bit closer, right? But so we get this kind of I don't want to say smoothed out, right? But it is kind of smoothed out forecast, right? And so it just kind of makes adjustments as we get more data. So just like before, and I think I've got it all in here. And by it all, I mean from last day. Oh. If we talk about the forecast accuracy, right, because we're using the same example data, the gasoline sales, and so we can compare values of the MAT, the MSE, and the MAPE, right? And so what we have, right, is now n-3, because 3 is the number of the moving average, right? And so here, this is because we have a 3-week moving average. Whereas before, when we had n-k here, then we just said, well, k is 1 because I'm using the previous value as my forecast. So I don't have one in the first row. I was thinking column, it's not the column, it's the row, right? So we don't have a forecast for the first value, and now we don't have a forecast for the third value. And even if you had to kind of sit back and find the average forecast error, then you wouldn't divide by 12. You would see that there are only 9 forecast errors, right? So you would use 9 as your denominator. So we get these different values, right? And so if we used, so from before, if we do a comparison between the most recent observation, right? And so here, if we do versus the most recent, and maybe I'll do, oh, didn't know that was possible. Okay. I'll call it the naive method, right? Then the MAE we have, and I'm just grabbing it from down here, but I just want to be able to compare them, right? So the MAE is 3.73. The MSE was 16.27. And the MAPE was 19.24%. So we notice that the 3-week running average is performing better with all these measurements, right? So oops. The 3-week moving average yields better forecasts, right? Better forecasts than the naive method. For example. So that's what you would do, right? It becomes a lot of different models. And so you want to name them all something different, and then you want to be able to compare them. And as you get something with a better mean squared error, so a lower mean squared error, right? We want to minimize the mean squared error. Then you can replace that model with that one. Someone's feeling hectic. So even with K, so we looked at a 3-week moving average. We could have looked at a 2-week moving average. 1-week moving average is what? That's just the naive forecasting method. So we wouldn't do that, right? But we've got 2 weeks, 3 weeks, 4 weeks, 5 weeks, 6 weeks. We could go up to 12 weeks, which would be the running average, right? And so which one do we choose? Well, you'd have to run all those models and look for the one that minimizes the mean squared error, right? So it's all about trial and error, right? And the one that minimizes the mean squared error. Okay. So you would run it with a 2-week moving average, 3-week, 4-week, 5 weeks, 6 weeks, probably through all the weeks, just to be sure, because then you have the running average, right? May as well. And so then you would just pick the one that has the lowest mean squared error, right? It means you have to run all those, but they take seconds, and it's really just a matter of copy and paste, right? Your code. But like I said, I'll show you how to do it, and it's not going to be so bad on Friday. Because it turns out, and I guess I skipped too fast, it turns out after trial and error, we find that actually k = 6 is the one that minimizes the mean squared error, and it minimizes to 6.79, right? If we find a method that gives a smaller mean squared error than 6.79, then we would consider that method, right? Because it seems to be better. So the running the moving average, I should say, not the running average, the moving average was kind of familiar from the running average. The exponential smoothing, not so much, but the exponential smoothing, what it does is it takes the actual value that happened previously and gives it some weight. And then it gives the old predicted value from the previous value, right? And it gives it some weight, right? So depending on what you think is going on, right, then you can have this, we call it exponential smoothing forecast. So the exponential smoothing is really just a weighted forecast. Okay, so the alpha is the smoothing constant, and it's the actual weight. Yeah. And so what we're trying to do is we're trying to forecast for t+1. So the t+1th observation we're trying to build a forecast for. What it does is it takes the previous observed value, right? Because if we're looking at, you know, weekly sales, then we have the sales from last week, the actual sales from last week, and then we want to apply some weighting. So we want to apply the rest of the weight to the forecasted value from the previous week, right? And so what happens is when you're looking at the previous value and the previous forecasted value, especially, then you have information from all the other observations in those values, specifically the forecasted value, right? Because it was forecasted on the previous value, and then that value was forecasted on the previous values, right? And so on and so forth. So you've got a lot of information there. And so what we do is we say, okay, well, what if I take some alpha, right? And this is different from the alpha level, right? In hypothesis testing, so the context will make that clear, but this is an alpha, which is the smoothing constant. And we pick an alpha between 0 and 1, right? So 60-40 would be 0.6 and 0.4, right? 1 minus 0.6 is 0.4. And so you would have the smoothing constants, of course, would add to 1, right? So you split. How we determine the alpha is, again, trial and error. Now, of course, software is going to help us out with that. But in the end, it's going to be trial and error, and you try different smoothing constants. And I just got a little bit of guidelines at the end, but I want to show you what it looks like. Or maybe I don't have one for this one. Oh yeah, I found I shouldn't have included this because I'm not actually illustrating it. That's what I wanted to remove. Okay. So to start, because we're depending on the previous observation, or I guess kind of the current observation, and then we're forecasting the next one, right? And so for week 1, let's say, so time equals 1, then we don't have a previous observation, right? And so what we do to initiate the calculations, oh, keep doing that. We let y hat 1 equal the actual value of the time series in period 1. And so we start off and we observe what happened in week 1, and then that's our forecast as well. We're really good at forecasting in week 1, right? And so, okay, let's see if I have, can't remember. Oh yeah, I do. This is the one I wanted to just have a look at. So here, if we have a smoothing constant of 0.2, so alpha equals 0.2, then what are we doing? Then the forecast for time 0.2 is the same as time 0.1, right? And so here, right, we see, are those on the same line? They must be. I just can't draw very well. They are. There. Okay. And so we start off our forecast. So our forecast for week 2 is whatever happened in week 1. Okay. And then for week 3, then we take some distribution of 0.2 times the previous actual value plus 0.8 times the forecasted value, right? And so it brings us up here, right? Because we only put a weight of 0.2 on this high one and 0.8 on this lower one. So it only draws us up a little bit, right? And so you can see how this really, really smooths things out. And so that's why it's called exponential smoothing. Okay. So here's kind of just a fun fact. It's not, crazy important, but when we're using the previous values, right? And so the first forecasted value is the first observed value, right? And so we've brought that information into the forecasts, and then we're forecasting based on the previous value that we saw in the previous forecast, and so on and so forth. And so all past data do not need to be retained to compute the forecast for the next period, right? We see that we only really need y hat t and yt, the actual value in the forecast. So if we have week 1, 2, 3, and 12, all through 12, then we have this first value, right? 17, and that's where we start our forecast. And so this comes down here and becomes our forecast for week 2. What if I have to do the forecast for week 3? So then remember, y hat t plus 1 is alpha times yt plus 1 minus alpha times y hat t. Right, and so here, this value would be y hat 3. Okay. So then y hat 3 is alpha times y2, right? Because it's the previous observed value, plus 1 minus alpha times y hat 2. Okay. If we let alpha be 0.2, let alpha be 0.2, then what we get for our forecasted value here is 0.2 times the previous value, right? So the previous observed value is 21, and the previous forecasted value is 17. So 21 here plus 0.8 times 17. And I really hope that works out because I haven't checked it. plus 0.8 times 17. Phew. Can you imagine if it hadn't worked out? 17.80. Okay. And so that's how we get it. But you can see how you're using the previous values here. Okay. And so then you would have your forecast, which means that you have some forecast error. And then we can find the mean squared forecast error, right? Because if we have the squared forecast error is the squared forecast error divided by n minus k, which in this case is 98.80 divided by 11. Because we didn't forecast the first week, but that's it, right? And you could just take the average of these, right? So you could just take the average, add up 16 plus 1.44 plus 24.6, blah, 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 blah. It gives you the total, so that's why I'm just jumping right to it. But what we get is a mean squared error of 98.8 divided by 11, which puts me at 8.9818 repeating. Okay. Comparing this mean squared error to the moving average, the 3-week moving average had a mean squared error of 10.22, right? And so our exponential smoothing forecast method is better, right? Because it has a smaller mean squared error. But I think compared to the moving average with k equals 6, so the 6-week moving average, it reduced the mean squared error to 6.79. So it would still be the best forecasting method in this case, right? So it's a lot of compare and contrast. So we can compare the MSEs to select the best forecasting method for this data. We've got the naive one. Naive had a mean squared error of, I want to say, what did I have here? 16.27. The 3-week moving average had a mean squared error of 10.22. And then we know, because it said the 6-week moving average had a really small 6.97, but I'm going to confirm. 6.79. Close enough, right? Not really. And then finally, the exponential smoothing. We should specify that alpha is 0.2, because we could play around with those alphas and find the best alpha to use, right? But here we have a mean squared error of 8.9818. And maybe I'll just cut it there. Yeah. Nice. So out of these ones, we would still pick the 6-week moving average, right? So this one minimizes the mean squared error. So that one is the one that we would pick. Okay. Let me just see where I can. Okay, yeah, this is the one I wanted now. It's almost like I planned it. Oh. Page break. Okay. So this derivation is not going to be important, but what I'm getting to is how do we decide what a good alpha would be, right? One thing you could do is you could consider, you know, all possible values of alpha. That can happen, right? You would map all the values between 0 and 1, or reasonably between 0 and 1. And then what you would have is you would have the mean squared error, and then you would pick the smallest one. So you can minimize it using our typical methods. If you've done some sort of calculus, then you could take the derivative if you have a function, and you can minimize it that way, right? And so for us, we're not gonna deal with that, right? But there are methods out there that you could use. And so here, right, we just picked 0.2, where I'm sure there was some reason that they used 0.2, alpha equal 0.2, but you would want to play around with it to see which alpha you should be using. And so how we pick alpha depends on the error term. Okay, so the forecasting errors that we expect. Okay, and so what we can do is we can expand out this exponential smoothing model. Right, we can expand the 1 minus alpha onto y hat t, and then we can rearrange, and then we have alpha times, so we have the forecasted value for time point t plus alpha, which is that smoothing constant, right, times the yt, the observed value at t, minus the forecasted value, which is the error, right? And so we can rewrite it as the error at time t times alpha. Okay, and so really in words, right, is that the new forecast is the previous forecast plus an adjustment, right? We're, you know, making an adjustment based off of the error that we had. Okay, and so the key here is that if the time series contains substantial random variability, then you should be using a small value for alpha, right? And remember, alpha goes between 0 and 1, so small would, I mean, arguably be less than 0.5, right? Maybe 0.2 or something like that, right? And so it explains here, right? The reason for this choice is if you're getting forecast errors because there's a lot of activity in your data, right? You don't want to make adjustments every time you have a forecast error, because you're expecting forecast errors because there's a lot of variability, right? And so so then you wouldn't want to put a lot of weight on those forecast errors. However, right, if you have relatively little random variability, right, there's always going to be some, but if you have, you know, kind of a steady activity with not a ton of variability, then you want to pick up on a forecasting error, right? A larger forecasting error should be like, whoa, what's going on here? What's happening? Kind of a in headquarters type of deal, right? And so for a time series with relatively little variability, right? And so then a forecast error is more likely to represent a real change in the level of the series. And that's where we're going to see that change from, okay, maybe we're hanging out here steady, 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 and then we see a change, and then we hang out again, right? Something like that. So then, right, I guess I should keep highlighting here. Larger values of the smoothing constant quickly adjusts the forecasts in the time series. Okay. So again, just like before, right, you're going to play around with different values of alpha. You could run it through all possible values of alpha, but there's going to be some value of alpha that minimizes the mean squared error, right? And so you could play around with different values of alpha, even with the data that we have, right? You don't need software. We have the data and you can play around with it. It's just going to be a lot of work, right? You could find the forecast value, which means then you have the error, the forecast error. You can square that forecast error. You can add them up. You can take the average. You can do all those things. You can do them by hand, right? When I say by hand, I mean with a calculator, but not using software. Right, and so you can imagine not too long ago when we didn't have computers, you can just imagine how much work went into finding these models, right? Now we don't have to do that. We can just type our code in. Okay, good. So the key here is that we want to minimize. We choose the value of alpha that minimizes the mean squared error, right? I just want to emphasize that just one more time. We have those other measurements, but at the end of the day, the one that we really want is the mean squared error. Yeah. Okay. So we've already talked about regression in chapter 7, and here it is again, right? Because what we said about regression was we're going to use it to predict future values, and that sounds a lot like forecasting to me. Now the problem becomes, again, we have this dependency among our observations, so we shouldn't really just flat out use linear regression, for example. As long as we recognize that we have this dependency, then we can use it, right? So we can start with a linear trend prediction, which is exactly what it sounds like. It is a straight line, so a linear model of the data where the independent variable is T, even though that's how we phrased it earlier, right? So you probably thought about, okay, my scatter plot would have some response Y and some independent variable T, but we never actually went ahead and did a regression, and now we are, right? And so, so the other methods were really relying on historical data, right? Whereas now regression doesn't necessarily, it builds on historical data, right? But we can use it to predict values in the future, right? We're extrapolating, we understand that, because we're not using values of X inside the range of our X's that we built our model on, but it's still our best guess. Okay, so we've got, oh yeah, and I want to go back and grab the bicycle sales. Where is it? There. So if you have, maybe I'll make this a little bit smaller here, there. If you have something like this, there's a trend here, right? So things are going kind of up and up and up. And if I had to model this, I would describe it as some sort of upward trend. To keep things simple, I'm going to call it a linear trend. I'm going to play around and look at different models, right? But one way that I could describe this is with a straight line. Does a decent job, right? One thing you want to look out for is this is over years, so over 10 years. There doesn't seem to be anything cyclical going on here, right? It kind of, it does have a wave. There's always going to be some sort of wave, but there doesn't seem to be a pattern. You know, every 3 years something happens, right? It goes up for 3 years and then it went down for 1 year and then it went up for 4 years and then it went down for 2 years and then it went up for 1 year and then we're done, right? And so there's no cyclical pattern here. And it can't be seasonal because it's over more than a year. So we've got this trend here, this upward trend. Okay. So what we're going to do is we're going to fit this linear model, which is just a straight line, right? Where we've got the intercept, the y-intercept, and the slope. And those are coefficients that we're going to estimate. And t is the independent variable, which is the time period. Okay. So again, we know from chapter 7, right, that I'll just go for it there. That's the problem. When I was highlighting in school, I would always highlight the entire page. Not very useful, but I'm trying to keep it to the ones that to draw your eye to it. So we know that regression, linear regression, maybe I'm not the only one here. We know linear regression, it minimizes the residuals, right? It minimizes the sums of squares of the residuals, right? The least squares regression line. And so then what that means is it's also going to minimize the mean squared error. Okay? And so we can use it and we can still apply, we can still have a mean squared error that we can compare to the other models, right? One thing that I want to highlight though is that the previous methods apply to only horizontal trends. Okay, so whether there be a break, right, then, but it can't handle something like a trend. Okay. So we can fit a linear model to it. Cool. And maybe I should have grabbed it, but I'm too far gone. Some output. So if you run a linear regression analysis, or if you fit a linear model, which I know I keep saying on Friday, but I'll show you how to do it on Friday. It's really not terrible. When we run a regression, we get this regression output, right? We've got the coefficient for the intercept, we've got the coefficient for the year, which is the time, right? And then even though it's kind of hidden, I guess, the MS residual, which is the error, is here. So we have a mean squared error of 3.8375. That's really low, right? And so we're not comparing, we're not looking at the same data anymore, so we don't have anything to compare that to, but that is the value that we would compare, right? If we're trying to pick a forecasting method. Yeah. So one thing, we're not relying on previous values anymore, right? So we can still find the mean squared error, we can still find the mean absolute error, and we can still find the mean absolute percentage error, the MAPE. But because we're not relying on previous observations or previous forecasts, then you can just let K be 0. There, good enough. We can also make more complex regression models, right? If you have some sort of curve, then maybe you want to have a squared t term, right? Or if you want to go really crazy, you could have t and t squared and t to the 3 as individual predictors. All right, so here, these are 3 individual predictors, but they all use t. But they all use t, right? T squared, t to the 3. And so that's how you're going to get some curve, and you'd play around with it. And that's how you would get some curvature into your model. Now, one thing I will say is if a linear model is going to suffice, then don't go crazy. Don't build these crazy models, because interpreting t squared and t to the 3 can be a little bit weird, right? So if you have t to the 3 in there, then you would have to say that, oh yeah, the effect of a year to the power of 3 is 0.4 or something like that. That makes it hard to interpret, right? And our goal is to interpret the results to our client, right? And so you want to avoid having to really get into nitty-gritty stuff. So if you can find a simple model that's easy for you to explain, that's the one to use. Okay. We could also do something crazy like if we built the model and then we could use the previous values. So if we're trying to predict the response at time point t, we could build it using the response at time point 1, at time point, t minus 1, so the most recent value, t minus 2, second recent value, t minus 3. So it kind of becomes this moving average situation, but not really at all, right? But it's the same idea, right? We're building off of previous values. And in this case, they're all predictors, but then you definitely don't have independence, right, among the observations or even among the predictors. And so that can be a problem. And so I've included a note about that. But when we have these auto-regressive models, which is auto means self, right? And regressive means that it's just regressing on itself. And so then those can get really complicated, right? And it's definitely beyond the scope of what we're doing here. So I'm going to include that here. It is a possibility, but I don't really recommend it. Yeah. That's really if you have a strong sense of, okay, what happened last week? I need to incorporate that into my model, right? What happened the week before? I need to incorporate that into my model, right? Because it's going to give me something. Right? So if you have seasonality, whoops, seasonality without trend, we'll start there. So seasonality without trend, and I'll grab the graph. It's from the beginning where we introduced the shapes, right? So here, I think it's this one, copy. Right, we have to know the shapes to know what to apply. So here, if you see seasonality without trend, right, that would be something like this. In fact, if you looked at this, it would be really easy to say that, okay, well, this is a horizontal pattern, right? It looks like there's random scatter around some average value, right? But we also need to understand that umbrella sales, right? So when we think about umbrella sales, then we suspect that there is some seasonality, right? And so since we have knowledge about umbrella sales, we expect, and that's just like common knowledge, right, about umbrella sales. If it's rainy, if it's a rainy season, then we're going to sell more. If it's not rainy, we're not going to sell any, etc. Right? So since we have knowledge about umbrella sales, we expect a seasonal trend or a seasonal pattern even if at first glance this looks like a horizontal pattern. So we have to be really, really careful. So if you want to incorporate this seasonality, right, it's going to be linked to some method or some measure of time, right? For example, if it's quarterly, right? So here we're looking at time periods 1, 2, 3, 4, and then 5, 6, I don't know. And then it seems to repeat itself, right? And so we seem to have this kind of seasonality this way. And what we could say is, well, let's play around with the quarters, right? So what you would do is you would make k-1 dummy variables, right? Because that's how we deal with categorical data, right? Is it in quarter 1, quarter 2, quarter 3, or quarter 4? That's a categorical variable. So now we create 3 dummy variables, right? Because the 4th dummy variable is just going to be with all of them turned off, right? And then that one's turned on. So then we could build a model, right, where we forecast y at time point t to be some intercept plus some coefficient times quarter 1. So that's on if it's quarter 1, and then the rest would be off, right? Or if it's not quarter 1, maybe it's quarter 2, then quarter 2 would be on, right? Times its coefficient added to the intercept, the other 2 would be off, and so on and so forth, right? And so depending on what quarter you're in, right, you would have a different line. Of course, we could have a combination. Let me grab the graph before I scroll down. We often have a combination of seasonality and a trend, right? And so, wow. So what we would do then, whoops. Is we would incorporate both aspects. Okay. So here what we would do is we would combine the dummy variables, which account for the seasonality, right? And then we would add the t, which is the trend variable. It's the time variable, but that's what gives us the trend, right? So here, this is the seasonality portion. And then this is going to give us the trend portion. Because remember, the trend we modeled by just a simple linear regression, B0 plus B1T, right? And so that would be the trend portion. And then now we're adding this seasonality component where we adjust for Q1, Q2, Q3, but then it becomes the same thing. So the hardest part is really identifying what's happening in here. And you'd want to play around with your models. You're not just going to pick one model and go with it. You would build likely hundreds of models to try to pick the one that performs the best, most consistently. Right. And so for other seasonal time periods, such as monthly, we would need to create 12 minus 1, which is 11 dummy variables. Right, so it totally depends on how many seasons you have, right? Quarters, you have 4 seasons. Monthly, you have 12 seasons. And so you'd have to have the number of seasons minus 1 dummy variables. Yeah. Causal variables I'm bringing up, but I'm really, really cautious because it's really important that we, and I'm going to highlight it right away, that the forecasting model is only ever going to give us evidence of an association, right? It's not going to give us a causal relationship where we think that there's a causal relationship, and that's why we call it a causal model. But all we can actually say is that there's an association, okay? And so what we can do is we can incorporate things like non-time variables, right? Advertising expenditures, when sales are going to be forecast, but maybe there's a time component, right? And so so we would incorporate those variables as well, right? Not necessarily just time. Okay. I just want to make sure that I can wrap this up, but that's basically what's going on there. And okay, I think we just might get there. So if we have causal variables, which are the ones that we discussed earlier, we can combine them with trend and seasonality effects, and we can build this really hefty model, right? We can incorporate non-time variables, right? We can incorporate trend variables over time. We can incorporate seasonality, right? And so, right, we can build a bunch of different wild models. Okay? If we suspected that sales were related to advertising expenditures and that sales showed trend and a seasonal effect, we can incorporate each into a single model, right, by combining these approaches, right? If we believe that the effect of advertising is not immediate, so this is kind of something that happens a lot, right? you might see, okay, well, you're not going to see an improvement right away, but you will see an improvement in 2 weeks from now, for example, right? And so then you could also try finding a relationship between sales in period T and advertising in the previous period, or maybe 3 periods back, right? But then you're incorporating previous data again, and we call that a lagged variable because it's lagging. So what's difficult about modeling is it is a lot of trial and error, right? And so you have the mean squared error, you have other measures of how good a model is, but one thing to keep in mind is you could build this crazy model. It's huge and it incorporates everything in your historical data, but then when you apply it, maybe it doesn't work so well, right? And so one thing that you want to be aware of is you don't want to be overfitting. And we've talked about that before, right? Where we are overfitting our model to the sample data, right? We have the sample data and we build this amazing model that describes everything that's happening in there. But then when we go to apply it, it doesn't work, right? And so we've overfit our model. Okay, and so what's really interesting is that a lot of studies have been done where if we're using these simpler models that we've introduced here, we haven't talked about anything truly complex. So if we're applying some of these simpler models, then they often outperform the more complex models. Not always, but usually, right? And so the tools that we have here they're plenty, right, for what we want to do. So that's kind of interesting, but also something to keep in mind, right? And so unless you have a really good reason to have a really big complex model, then just stick to the basics that we've talked about here. So how do we pick the best model? I'll kind of leave this for you to read through, but one thing you could do is you could have a training set, right? So you could do some cross-validation where you divide your sample into a training data set and then a validation data set, right? And so then you can build your model on the training and then you apply it to the validation set and then you see how well your forecasts are doing, right? And so because those haven't been incorporated into your model yet, and you're always looking at the mean squared error, you can consider the MAPE and the MAD to pick the best forecast method, right? One thing to keep in mind though is that if you simply divide your data, your sample into the oldest data, and then so you train it on the old data and then you apply it to new data, then something might have happened in between, right? So you want to take a random sample. Often that's not possible, right? But you want to do your best. Okay. So I can see I'm really out of time, but that's an introduction to time series. There you go. If you have any questions, let me know. Otherwise, I will see you on Friday to practice some of this in R.